What? 2, 3 after this? Yeah.
Yes. Hey everybody, we're back. Part 2 of our recording for today. So, that's true. I guess it is kind of like part 3. So, well, we're here this morning, and I had because they have to take an exam in 2 weeks, and so. Where is my pen? Oh no. Oh, there it is. Woo! Okay. All right. So here it says diagram below represents. Oh, sorry. Just gonna. Psst. All right. So with this question, while you guys had some time today, I put together more review problems on waves. The stuff that's from Caboodle, so I'll have that out to you later today. It won't be all the review pages like we talked about, but it will be like the sample problems from the book, so that you can, if you want to do some more wave stuff as we go along. Okay? Here, right, just identifying different things from the picture. What is a wavelength? What is amplitude? And then this relationship again for speed, right? We said that there's 2 ways we can calculate speed. One is frequency times wavelength. The other one is wavelength over the period. Both of them will work.
I'm so upset.
So, let's do this. So, all right. The diagram below represents the direction of oscillation of a disturbance that gives rise to a wave. So this is the disturbance itself. Okay? So it says, by redrawing the diagram, add arrows to show the direction of wave energy transfer to illustrate the difference between a transverse wave and a longitudinal wave. All right? Here, nope. Right. Sorry. We're backwards. Does that make sense? Right? For a transverse wave, the medium moves at right angles to the direction of wave transfer. Right? For a longitudinal wave, the medium moves parallel to the direction of wave transfer, or energy transfer. So in this case here, as we make that disturbance this way or side to side, the energy transfer is going to be either up or down or front to back or whatever for a transverse wave, but in a longitudinal wave, they have to be parallel to one another. Parallel, perpendicular. Good? A wave travels along a stretched string. The diagram below shows the variation with distance along the string of a displacement of the string in a particular instant in time. A small marker is attached to the string and the point labeled M. The undisturbed position of the string is shown as a dotted line. All right, so the equilibrium position is that dotted line. Right? Draw an arrow to indicate the direction in which the marker is moving. Good. Indicate with letter A the amplitude of the wave. You probably can draw a little arrow there too, right? Indicate with letter lambda the wavelength of the wave. There's a couple of different ways you could do this, just to keep it clean. I'll go here to here. All right. But there's a couple different ways that we can show that wavelength, right? Crest to crest, trough to trough, or if we wanted to go through the middle, we just have to make sure, right? That's not a wavelength. We got to go up and down, so it would be the whole thing, right? Draw the displacement of the string time t over 4 later, where t is the period of oscillation of the wave. Indicate with letter N the new position of the marker. All right. So in this case here, for the last part, letter N indicate the new position of the marker. I'm gonna go there. All right. Does that make sense? Did I do that backwards or no? No, it's good. Did I do that right? No. So the wave is going that way, right? Does that make sense? All right. So 1/4, it's, where is it? T over 4, right? So it's 1/4 of a period. So everything is basically going to be shifted 1/4 of the wave next, right? So this is going to be over here. This is going to be here. This is going to be here. This is going to be here, and this is going to be here. Does that make sense? Yes, no? Do I need to connect the dots? No. Does that make sense? Yes, no, maybe? Okay. So then this would be N, that would be the new position of that marker because it's just going to move up and down, right? Like I said, T over 4 is 1/4 of a wave, so that's going to be basically everything's going to be shifted to the left 1/4 of where it was before. All right. Any questions? We good there? Okay. Wavelength of the wave is 5 centimeters, and the speed is 10 centimeters per second. Determine the frequency of the wave, how far the wave has moved in T over 4, or 1/4 of a period, right? So again, getting back into this part, right? They gave us the speed, they gave us the wavelength, we just have to find the frequency, right? And so the frequency 2 hertz. And then part 2 is asking us about the relationship between frequency and period. Frequency and period have an inverse relationship. So if you can figure out the period of the wave by taking the reciprocal of the frequency, so that means the period is 0.5 seconds. Good there? Right? But that's not what this question asked us for, right? It was asking us about 1/4 of a period, right? T over 4 is 1/4 of a period, okay? So that means they want to know how far the wave moves in that many seconds, right? You know this is the speed. You know this is the time, so we just go back, right? Speed is a relationship between distance over time, v, s, whatever, right? And so did I do that right? In my head? Nope. Multiplying something by 10, it can't be that hard. So I don't trust myself. Say again.
I got the 25.
Okay. Okay.
Well, we did that part.
Okay. But do you understand why the okay, you got this good, and then yeah, it was just this part here. Just my guess would be probably that'd be 1 point out of the 2 for this problem. You know, because like you got this part because that's the first thing you need to really figure out is what the period is, and then doing this part is that would be my guess, although I don't know for 100% on that. So. And that's fine. So, all right, good with that one. Okay, let's. Oh, one more before we get into the confusing part. Okay. I really think this should be another question, but they apparently call it the same. Yeah, and I think it obviously it relates more to this stuff than it does to this stuff. So I really think that probably this should be the start of the new question, but that's not what they did, so whatever. Okay. By reference to the principle of superposition, explain what is meant by constructive interference. This is 4 points. It doesn't seem like there's a whole lot there, but let's break down the question and make sure we hit all the right parts, right? So the first thing it tells you is what? Reference to superposition. So you gotta mention superposition, right? What do you remember what superposition is? Anybody? Waves on top of each other, right? Two waves, two or more waves can exist at the same space at the same time, right? So first thing you gotta do, right, is talk about what superposition is. That's gonna be 1 point, okay? All right. Constructive interference. Let's start talking about other things that we need to discuss, right? What happened? Oh, sorry. That's actually probably the second part here, okay? More than one wave can exist at the same point at the same time. What is the overall amplitude of those interfering waves? It's the sum of the amplitude of the two waves. That would probably be points 1 and point 2, okay? That superposition says you can be in the same place at the same time, and when that happens, we have amplitudes that add together. That would be my guess as far as point 1 and point 2 on this 4-point question. Okay? Okay? Points 3 and points 4 there. When we talk about constructive interference, what happens to the amplitude, or how is the resultant amplitude? It's an increased resultant amplitude, right? You have a greater resultant amplitude than either of the two amplitudes individually. And that's basically going to happen in one of two ways. What do we have to meet up to get constructive interference, or the maximum constructive interference? To what? 2 crests or 2 troughs. Even though troughs are below the equilibrium position, that's still an increased amplitude. It's just an increased amplitude downward, right? So, right, even this simple sentence, if we break down the 4 points, right? Superposition. Waves can exist in the same place at the same time. When that happens, we have a resultant amplitude that is the sum of the individual amplitudes. Constructive interference is when we have a bigger resultant amplitude, or an increased resultant amplitude, because crests meet crests or troughs meet troughs. Okay. Is that good as far as the 4 points go? Okay. All right, well, let's talk about this, okay? So, these pictures are representations of Young's double slit experiment, all right? Going up here, these pictures represent wave fronts. Those are the arcs, right? Okay? A ray would be something that looks like that. Okay? A ray always has to be perpendicular to the wave front. Does that make sense from the picture, right? Okay. When wave fronts of different waves run into each other, because of superposition, they will interfere. Depending on whether we're meeting crests and crests or troughs and troughs, that's going to result in either constructive interference or destructive interference, right? Here you can see, right, constructive interference, constructive interference, constructive interference when two wave fronts run into each other, right? But there are these spaces here that are marked with destructive interference, right, where you're getting the crest of one and the trough of something else meeting up, okay? What we find is that in Young's double slit experiment, first, monochromatic source of light, right, the same frequency, meaning that this distance and 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 this distance are going to be the same on both sides, right? That's going to be monochromatic. Now, if we're talking about light, that would be monochromatic, it would be the same frequency, the same color of light. If we're talking about sound, it would just be the same pitch, right? The same frequency of sound. We can do this with sound as well, okay? But same thing happens with any kind of waves, whether they're light waves or whether they're sound waves, right? You start getting these spaces of interference, right? And so you got interference here, and interference here, and interference here. Those are constructive interferences, right? Superposition leads to increased amplitudes. But, and I'll use a color here to try and show this a little bit better, okay? If we were to draw a perpendicular surface, it's a screen, it's a wall, it's something, okay? What we find is that along that screen or wall, we get certain areas where there are constructive interference, like right here, right? And then certain areas right here. That's the biggest one, but it happens along the way. We will get certain areas along that wall where the waves interfere constructively, and certain places where they interfere destructively. And what ends up happening is we get a bright spot and then a dark spot right next to it. Constructive interference leads to a bright spot because the two waves are constructively interfering to make it brighter. If they destructively interfere, right, trough cancels out crest, and then we don't have any light. So we have this pattern of light, dark, light, dark, light, dark. We call those fringes, all right? Here is an explanation of why that happens, all right? In order for there to be constructive interference, the wavefront from this opening and the wavefront from this opening have to meet up at that spot right there, okay? Now, here's the deal. In the review book put out by the company, and it says right on the cover, right, for the IB diploma, it's from Oxford. This is a company that works with IB, okay? It says right here, the location of the light and dark fringes can be mathematically derived in one of two ways. That's one of the ways up above. But then it says directly after, the derivations do not need to be recalled. And yet here it says, deduce an explanation, or an expression for these different terms. So, this is like, here are the step-by-steps with what they go through, okay? I don't know if I would put in the time to memorize how this goes, okay? This is the important end result, okay? S, little s, is the distance between where the bright spots show up on this wall, okay? Or the distance between the fringes, okay? Lambda is the wavelength of the light. If it's monochromatic, it's the same wavelength for both. D is how far away the screen or the surface is from where the waves are being originated, or at least from the slits. And then little d is the distance between the slits. Okay? One assumption that we make in this instance, the distance from where the slits are to where the screen is much, much larger than the distance between the slits. Okay, that's the one assumption that we make out of this. Okay? Good with that as far as the breakdown goes. Okay? Right? This is just a bunch of algebra. Alright? If you don't know this, like, if you don't know all this stuff right off the top of your head, trying to go through the process of deriving it on the test is probably going to take more time than it's worth. Does that make sense? Right? Say again? Yeah, and it's only 5 points, right? So, I mean, not that that's not a lot of points, but right, the superposition question was 4 points, and now you could answer it in way less time than you can answer this. Unless, like I said, unless you have this memorized, I don't know if the time to go through it during the test is going to be worth the points that you would get out of it. All right? Now, this expression shows up in your formula booklet. Okay? This is straight from the formula booklet. Okay? Keep in mind that we can only have this if we have differences in wavelength intervals, because wavelengths, crests and crests, meet up at an interval equal to the wavelength. Did that make sense the way it came out of my mouth? Right? So here, crests and crests aren't meeting up because the interval is 1/4 of a wavelength. If we moved all of this down one wavelength, it would match up with the wave that's already there, right? So we only get the constructive interference if we have an integral, that's the word I'm looking for, integer difference in wavelength, all right?
So otherwise nothing happens.
Otherwise, you're not going to get the distinctive light, dark, light, dark, light, dark. It would be grayish, You'd have some areas that were brighter than other areas, but you wouldn't have the distinctive light, dark, light, dark, light, dark pattern that shows up with this monochromatic light at those intervals, right? That's the biggest thing. You'd have interference, but it wouldn't make that nice repeating pattern, right? That's what would happen. What can?
Like where it's where's crazy going to
There might be a mathematical pattern there, but I'm not 100% sure if it falls.
like just going crazy.
Yeah, like there might be a pattern in there, but I don't know algebraically what would represent that pattern. So yeah, like here, this represents the pattern, where S is the difference between this light spot and this light spot. And if it's monochromatic light, then that's going to be a regular interval. Okay. Yeah, it's just light, dark, light. Yeah, there might be a mathematical model for something like that based on the difference in the frequency between the light or something like that. Like if you had two different frequencies coming out of here, right? There might be a pattern there, but I don't know what it is. So, all right. So it says here, for a particular arrangement, the separation of the slits is 1.4 millimeters. That's this. Okay. Distance from the slits to the screen is 1.5 meters. That's this. Okay. So it says the distance y sub n, that distance there, is the 8th bright fringe. Okay, so there are 8 dots in that space. There are 8 bright spots in that space. Not yet. Okay, so it says, using your answers to E, determine the wavelength of this light. Okay, here is the wavelength. Okay, but we don't have everything that we need to have to solve that equation just yet. All right? We have D, that's this distance. We have little d, that's this distance. We don't have S. S is the distance between each bright fringe. But we know that this distance is 8 times that. Excuse me. Okay. Does that make sense? Okay. So, say again. Big D is this right here. Is the, yeah, that's this one. So, my color, I'm mixing up my colors. So, right. And then little d is this number here. Okay. All right. But they did give us the angle theta. Okay. Which shows up right here, but that angle phi is also the same angle. Okay, you can show that mathematically if you don't trust me, you can. Okay. But using that, we can figure out what that distance is. Okay, you do a little trig because you know this side of the triangle. You know the adjacent side. You can try to find the opposite side. You use tangent. What? What? Yeah. This one's one of those ones that, you know, like the people who get like the 7s are gonna be like, oh yeah, I get it, you know. So, but it's on there. So.
The 10% of the
Yeah. So, if that. All right. I will send you guys the review stuff on the waves, very similar to a lot of the problems that we did in class. And then tomorrow we can start electricity. So 9:30 again tomorrow. Is that the plan? So, wahoo!